you. So in this work, we propose a private set intersection, and I would like to start by breaking down this title. So a private set intersection is the ability to perform the intersection of two or more sets, each one held by a different party, in a way that reveals only the intersection and nothing more. Typical private set intersection protocols, they consider two parties known as the sender and the receiver. The receiver is the one that actually learned the intersection, and the sender doesn't learn anything. And also in these typical protocols, they assume the parties to have sets of similar sizes. But there are applications, for example, private contact discovery. Let's say you are new to WhatsApp and you want to find which of your contacts is also on WhatsApp. So in that case, your set, which is your list of contacts, will be small, and the WhatsApp user base is large. So in this case, a protocol designed for unbalanced sets would be more efficient. And also, there is a case that you may be changing this small protocol, this small set many times, and you want to intersect against this large set again. So that's where the recurrent private set intersection protocol comes, and it would be inefficient if you had to run the whole protocol every time you do this new intersection. And Cuckoo hashing and level full homomorphic encryption are just some what we use to build this protocol. So there are several applications for private set intersection protocols, but I want to present here one example. That's what motivates us to do this project. So imagine you have your institutional email and someone sends you an email, and your institution wants to protect you against phishing attacks. So they employ some service of a service provider where they will check if any link in the email is malicious, like it's redirecting to some malicious website. So they will take this, your mail server will take this list of malicious, this list of URLs in your email and send to the service provider. The service provider will match this list against a database of malicious URLs. And if there is any match, it will inform the mail server, which will block and not let the email get to your inbox. Otherwise, if there is no match, it's all good, and the email goes to your inbox. The problem here is that we have some privacy issue here because the mail server is sharing all the list of URLs that you get in your email. And in addition to that, we can see that this operation where we are comparing the list of URLs in the email against the database is a set intersection. So we can use a private set intersection to make this private. And moreover, we have that the list of URLs in the email is expected to be small, like you just have a few URLs in an email that you receive, while the database is large. It's usually 1 to 2 million in practice for this type of application. And finally, while you may receive just a few emails per day, if you think about everyone in your institution, there are maybe thousands of people, so there are many emails coming. So the mail server will be doing this operation many times, so it's a recurrent operation. So what we develop here is a protocol for this setting, for the recurrent setting. It has a one-time cost on the large set and a linear cost in the smaller set. We propose several optimizations to reduce computation and communication costs. And with that, we get a protocol that's 1 to 2 orders of magnitude faster than the state-of-the-art, depending on the network speed. This for the target set sizes that we consider. So now I will go quickly over the protocol. Well, this is not the actual protocol that we propose. The one we propose in the paper is much more complicated and much bigger than this, so I don't have time to go over it in this presentation. So I will try to do the next best thing, and I will take this basic protocol, which is inefficient, and this protocol serves as like a blueprint to build that actual protocol. So we perform many optimizations to this protocol to get to the final protocol. In this case, we start with the two parties, the receiver, which is the mail server, and the sender, which is the service provider. Then the sender will encrypt its set with its own key. This uses all fully homomorphic encryption and sends it to the receiver. The receiver computes the intersection using the equation in 3b. This is, it performs a homomorphic subtraction of the element it wants to check against all entries in the sender set. If any element is part of the intersection, one of the subtractions will be 0. So when we compute the product will also be 0. Otherwise, it's non-zero. Then we add some randomness for security, and we send back this encrypted result to the sender, and we also encrypt this random value with the receiver key and send it to the sender. Then the sender will decrypt this result, subtract the random value. This is a homomorphic subtraction, and it's under the receiver key. So everything looks random to the sender. It will multiply by another random number, also for security, and we send this final result to the receiver who decrypts it. If there is a 0, it means it's part of the intersection. If there's no 0, then it's not. Now, in this protocol here, we have steps 1 and 2, which are one time, so you need to do only once, and steps 3 to 5, you need to do every time you get a new email. And here we have two issues. Like if we assume that the sender set is around 1 million entries, sending an encrypted set would take around 7 terabytes. And for each entry in the receiver set, it will require around 1 million homomorphic multiplications. So it's very inefficient. So I will show how we solve these two issues in this presentation. Let's go first through the linear search. To solve that, we just use hash. So it's very simple. So instead of having to compare against everything, we only need to compare where the value can be hashed to. We could use simple hashing, but because the way the values are distributed and because the way there is the load of the items are distributed, we need to pad these values with dumb values for security. So we don't get that much of a compact data structure. So instead we use Cuckoo hashing, which let us create a much more compact data structure because we use more hash functions to create these, to place these items in this structure. And besides this, we can also do other trickery with Cuckoo hashing that lets us reduce the communication cost, but I'm not covering that here. So when we apply Cuckoo hashing here, we reduce that linear search to a constant time search. We only need to do 3 multiplications for the parameters we use. And another thing is that because we reduce the number of multiplications, we can use more efficient encryption parameters, which reduce the ciphertext size, so it also reduces the communication. But 100 gigabytes is still a lot. So how we solve that? We try to pack as many entries into one ciphertext we can. So in fully homomorphic encryption, we have 3 spaces, the message space, and we use BFV, so it is an integer space, and plain text space and ciphertext space are polynomials. Originally, one would encrypt a single integer into this polynomial, which was very wasteful. So later, batching was proposed, which let you encode n entries, any messages into one polynomial, where n is the polynomial degree. And in this work, we propose to add on top of batching a packing technique that's based on the Chinese remainder theorem that let us pack k times n messages into a single polynomial. So when you do that to the Cuckoo hash table, we get that the encrypted table would get only 12.5 megabytes. And just for context, if we send unencrypted data, it would be 4 megabytes. So when we apply that, this is how we do the encoding, how it looks like. So the set X is the sender set. We do the Cuckoo hashing. We have several hash tables. This is also for security reasons, but not covering here. And then we encode it, and each table go to a different packing slot. And then we have ciphertext, which are the gray boxes, and each ciphertext has several batching slots. So if we put that to this protocol, we reduce the communication down then to 12.5 megabytes. Now, there are many more optimizations we add to this protocol, but I would say that these two are like the most impactful ones. And now I want to use the rest of the time just to discuss some of the results we have. So we look at to a sender set size of 2 to the 20, which is that X there, which is around 1 million entries. And for the receiver set size, we look at size 4, 16, and 64, because we don't expect to have that many URLs in an email, right? And we have 2 instances of our protocol. One is designed for fast setup, so this would be when you have fewer recurrences. So and the second one is for fast intersection, so this is when you have many recurrences for every update of the larger set. So in this case, we have that on fast networks, 10 gigabits, we have our setup does the one-time cost. Our protocol does the one-time cost from 0.1 to 0.3 seconds. And in slower networks, it's from 1.2 to 2.5. And when we go to the recurrent cost, so every time you do a new set intersection, we get as low as 20 to 30 milliseconds for very small set sizes. And when we go in slower networks, we get from 0.2 to 0.3 seconds to do the same intersection. And as comparison, just with related work, some of the related work, they don't have one-time cost. Everything is recurrent. And the ones that have one-time cost, we are a little faster on the 10 gigabits and a little slower on the 100 megabits. But what really matters is the recurrent cost, because this is happening many times. And in this case, we are up to 2 orders of magnitude faster on the faster networks on 10 gigabits, and up to 1 order on the slower networks. And this concludes my talk. The code's available on GitHub. Thank you.
Okay, thank you for your talk. Any question?
Thank you for your talk, really interesting. So what do you think is like the biggest limitations that you would like to plan to overcome in the future on this?
Okay. I think the issue is communication. In terms of computation, we are very fast compared to related work. In terms of communication, we are very good at compressing the larger set, but we are still not good at compressing the smaller set. So it means that communication in the recurrent part could be better if we could do that.
All right, thank you.
Other question?
Hey, thanks for the great talk. I'm just wondering, when the hashing takes place, does the sender learn which buckets the items are not from? Is that a line of leakage in this kind of a mechanism?
I didn't.
So who's doing the cuckoo hashing, right?
The sender is doing cuckoo hashing. So it's
Right.
on the sender does on its own set.
Commits on the set, right?
Yes, sender does the hashing on its own set. Yeah.
Right. And so when it sends it to the receiver does the multiplication or like the comparison with each set, right? Doesn't the receiver learn which sets they're not looking into at that point?
No, because the value can only be hashed to a specific location, cuckoo hashing to a few locations.
Mm-hmm.
So you would do the operation, that subtraction, in those locations only. If the value is there, one of the subtractions will be 0. But you don't know if the value is there. The value may not be there. So if the value is not there, something else is there. It could also just be a dumb value. So the receiver will not know where the value is. If the intersection is true, like if the value is part of the intersection, of course the receiver will know that item is also part of the sender set, but otherwise it doesn't learn anything.
I see.
I think I need to go into details
we
to
can speak offline.
explain.
That might be better. Yeah, for sure.
yeah.
Thank you so much, though.
Okay.
I have a last question. When you use, by using compression, you are compressing, in fact, the data from terabytes to 12 megabytes, if I remember. I suppose this depends on some parameter you choose.
Mm-hmm.
How did you choose them?
Okay, so there are 2 things there. One is related to the cuckoo hashing, which is basically what you need to choose. What are the parameters for cuckoo hashing that you use to try to increase the load factor in the cuckoo hashing? So in that case, it would be the number of hash functions you use. The more hash functions, the more data you can compress. You can put in the same size of the table, but it's kind of diminishing returns. And also, when you are inserting cuckoo hashing, you kind of need to, the way it works is that you insert, if there is an element there, you kind of remove that element and put yours, and then take that one and continue, kind of this recursion thing. And you need to put a limit to that. You cannot be doing that forever, because you may get stuck in a loop. And also, so the deeper this limit is, the more data you can also pack in the table. So this is one thing. And the other thing is related to how we encode the data into the plain text polynomial. So that's where that memory reduction comes mostly. Because of batching and this packing technique we have, we can put like thousands of entries into a single ciphertext.
Okay. Okay, thank you again.
Thank you.
Another applause.
Okay.